Hey guys, so this is the last lecture that will be on your test on Wednesday, okay? So you have a test Wednesday on chapters 14 and 15, and this is your last lecture that deals with that, okay? So the last thing we need to talk about in chapter 15 is Le Chatelier's principle. And I know that seems like a very weird title, but that's someone's name, okay? And basically the idea is you can't bully an equilibrium, right? You can't just push it around and the equilibrium goes, oh, okay, right? No, if you push an equilibrium, it's going to push back, right? Basically, we have this concept that equilibriums are going to keep the balance. And if you push it to the right, then it's going to push back to the left to cancel out a little bit of what you've done. Now, it's not going to be what it was before, but it's at least going to reobtain that ratio, right? The K, the capital K, the equilibrium constant, is not going to change unless what? What's the one thing we do that changes capital K? Temperature, right? If you add heat or remove heat, then capital K will change, but just increasing an amount of reactant or decreasing an amount of product or changing the volume, which changes the pressure, none of that stuff is going to change capital K, right? But we need to talk about all these effects of how all the different ways we could manipulate an equation, okay? So this is named after the French industrial chemist who actually discovered this, okay? And basically, the way we say it is this. If a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of any one of the species, reactant or product, the system will shift its equilibrium position so as to counteract the effect of the disturbance, meaning you cannot bully the reaction and it just stands there and takes it, it fights back. Okay, so then what are we talking about? We're talking about you have a system at equilibrium, and then you're going to make a change to it. And these are the 5 things we're going to discuss as the types of change you could make. You could change the concentration of a reactant or product by either increasing it or decreasing it. Volume and pressure go hand in hand, right? According to Boyle's law, they're inversely proportional, so we'll talk about them together. You could add or remove heat, temperature, and we're also going to talk about what happens when you add a catalyst, which you learned about last chapter in chapter 14. And the idea of a catalyst is, right, it speeds up a reaction. So does speeding up a reaction change the equilibrium? Not going to answer that for you now, but we will answer it in this lecture, okay? And then we're going to talk about how it responds, right? Is it going to, you're going to hear me say a lot, shift left or shift right. When I say shift left, I'm talking about towards the reactants. When I say shift right, I'm talking about towards the products. All right, so let's start with concentration because that's the first one, and that's kind of the easiest one to get. So you have a system at equilibrium, right? But remember, an equilibrium is a dynamic equilibrium. It's a dynamic state. It's when the rates are equivalent. So if you change a concentration amount, you're changing one of the rates. So it has to counteract that to re-achieve the equilibrium to get the rates the same again, right? So we have this statement: if a chemical system is at equilibrium and we add a substance, the equilibriums will shift so as to reestablish an equilibrium by consuming part of the added substance. Here's Dr. Stover's shorthand for that, okay? It's going to shift away when you add, okay? When you add, it shifts away. So if you add a reactant, it's going to shift towards the products. It's going to shift to the right. If you add a product, it's going to shift away. It's going to shift towards the reactant, which means it's going to shift towards the left because it is counteracting what you're doing. However, remember, we're only talking about the things that would be included in an equilibrium constant expression, and solids and liquids are not included in that, so do not include them, right? If you add a solid, that doesn't do crap. If you remove a liquid or add a liquid, that doesn't do anything, right? It has to be something that's in the equilibrium constant expression, which means aqueous ions or gases, right? Okay, so for example, if we add a reactant, that's going to decrease slightly the amounts of the other reactants so that we can create more products and find the new position. So here's a pictorial example of what we're talking about. So if we add more NO2, which in this case is a product, it's going to shift to generate more N2O4. So those NO2s are going to react together and generate more N2O4. What does that look like in a graph form? So we're plotting time versus concentration. So here we're at our happy equilibrium, and then boom, all of a sudden we've just dramatically increased NO2 concentration. So what's going to happen? Some of that NO2 is going to be consumed so that we can make some more N2O4. At this point, the rates are now equivalent again, and the concentrations aren't changing. You know, you could have flipped it. You could have added N2O4. And if we added N2O4, its concentration would dramatically increase, but then some of that would be consumed while some NO2 was being produced until the rates are now equivalent again. And once the rates are equivalent, the concentrations cease to change. Okay? So the shorthand is this. When you add, it shifts away from where you add. All right? Now, why does it do this? Because, well, when you add a reactant, it initially increases the rate of the forward reaction, right? But that doesn't affect the rate of the reverse. So your rates are no longer the same, right? So it has to shift to the right to get your rates to be the same, because the more products you make, the more you can speed up the reverse reaction, and they'll eventually meet up with each other again. Okay? So you have to reestablish when the rates are equivalent, because that's the definition of a dynamic equilibrium. Because these are dynamic equilibriums. They're not static. They're not stationary. They move. They change. Okay? But here's the deal. K is K though. You didn't change the temperature. So the Kc originally is going to be exactly the same as the Kc new. We are not changing the numerical value of capital K. Has the concentration of the products changed? Yeah. Has the concentration of the reactants changed? Yeah. But they either both went up or they both went down, and their proportionality to one another did not change, which is what K is. Right? Well, what about if we remove? I told you that if we add, we shift away. Then what do you think is going to happen if we remove? If we remove, it shifts towards where you removed. Okay? Because we've got to form more of the substance you took away. So if you remove a reactant, it's going to shift to the left to make more reactants. If you removed a product, it's going to shift to the right to make more products. Right? You got to make what you just took away. Okay? But the same thing again, right? It's going to change your rates. You have to reestablish those rates. But here's the deal. You have not changed K. Capital K has not changed because you did not change the temperature, and that's the only thing that changes the numerical value of capital K. All right. So that's concentration. What about pressure and volume? Well, I already told you that these are inversely proportional, right? Which means as volume goes down, pressure goes up. As volume goes up, pressure goes down. And this is really how we tend to change the concentration when it comes to gases. We just change the volume, right? And so think about it. Volume is going down, then the pressure is going up. So it seems like there's more gas molecules. We need to counteract that by somehow diminishing the number of gas molecules, because we need to have a lower pressure because we have increased the pressure too much, right? We have to counteract it. We've increased the pressure, so we got to figure out how to lower the pressure. The easiest way to do that is just to cut down on the number of gas molecules. So how we say this in Le Chatelier's terms is that when you reduce the volume of a gas mixture at equilibrium, it's going to cause the system to shift in the direction that reduces the number of moles of gas because you're trying to lower the pressure, right? So let's look at an example. Let's look at the production of ammonia from nitrogen and hydrogen gas, okay? So in this reaction, you have 4 moles of gas reactant and 2 moles of gas product. So if you cut the volume, you have dramatically increased the pressure. The only way we can decrease it is shift it to the side of this reaction that's going to generate the lowest number of molecules. 4 versus 2. 2 wins. 2 is fewer, so it's going to shift to the right, to the fewest amount of molecules. Whereas, what if we did the opposite? What if we dramatically decrease the pressure? Now we need to counteract this. How do you counteract decreasing it? Well, you need to increase it. So we're not going to shift to the right. We're going to shift to the left, to the side with more gas molecules. Because again, the idea is we are trying to counteract the change. Now, how this works though is it's based off of the, Boyle's law. It's based off of Dalton's law of partial pressure. But again, we're talking about gases. Gases, gases, gases. So what do you notice doesn't matter? Solids don't matter, liquids don't matter, and solutions, AQ concentrations don't matter. Okay? Because they are not playing a role in the pressure. Okay? They're not generating pressures. Only the gases are generating pressure. So changing their concentration isn't going to do anything here, okay? Because we are talking about things that have pressures, and what has pressures is gases. All right? So decreasing the volume, it only increases the concentration of the gases because it's not going to make a difference in terms of molarity, solids, or liquids. All right? And I've already sort of talked you through this, but let me be clear. There is one type of gas, though, that you can add or remove, and it won't do anything to the equilibrium. Okay? And that type of gas is what we call an inert, I-N-E-R-T, an inert gas. And what an inert gas is it's an unreactive gas. And you have a whole column in the periodic table of unreactive gases. What do we call that column? The noble gases, right? So the noble gases are inert, unreactive gases. You can add helium, it's not going to affect the equilibrium. You can add argon, it's not going to affect the equilibrium, right? Because those are noble gases, they're inert, they have no effect whatsoever on the equilibrium. Okay? And we're sort of reaching the end of the time frame for this video, so I'm going to pause now, okay? And we'll pick up with the effective temperature in the next video, all right? So, end of video 1, I'll see you in video 2.